All right, what is going on, chat? This is going to be the first video here on the channel, and we're just going to jump right into it. This is just like the general chemistry stuff we're just going to jump into. So a lot of this might be familiar to you guys already. So this is your electronegativity values, and let's just say you have a bond, so hydrogen and carbon, and you want to determine whether this bond is nonpolar, polar, or ionic. You get the two values of the two elements. So for example, in this case, it's carbon, hydrogen, and you subtract the two. And if it's less than 0.5, that's a bad point. If it's less than 0.5, then it's nonpolar. If it's higher than 0.5, then it's polar. But if it's higher than 1.7, then it's an ionic bond. All right? So less than over here is nonpolar. Over here, higher than 0.5 is polar. And then over here, past 1.7 is ionic. Now, you don't have to sit around and study this for like 500 hours. You might get like one question on it on your first like organic chemistry quiz. But other than that, you're probably never going to see this again, and it's probably not going to be helpful for you to like be a master at this. Like, I don't think I ever used this side. Maybe I used bromine and iodine, but just these guys right here are like we're probably going to be tested on. And then over here, as you can see, I put like a dipole, and the dipole just shows where the charges are in a way. So this plus end, or you might see it like this, where it's just a T. I like to do the plus just to show that this side right here is partial positive, and then this side over here with the arrowhead is partial negative. That's what a dipole is. It just shows which side is partial positive and which side is partial negative. All right. So that's about it for this side. And then moving on over here, this is how you're gonna see the elements be bonded. Like, I don't know if I worded that correctly, but that's how you're gonna see like carbon, nitrogen, and oxygen in your like Lewis structures or whatever, right? So you're probably wondering, why is there like all these random different, there's like 3 different carbons, 3 different hydrogens. Well, these are where the charges come into play. So there's a positive charge area here, a neutral charge area here, and a -1 negative charge row right here. So from your Gen Chem knowledge, you know that carbon has 4 valence electrons, nitrogen has 5, and oxygen has 6, right? So that's what this chart is representing. Right here, carbon has 4 valence electrons, so it can have 4 bonds. Why? Because it can fill out the octet rule, right? So now it has 8 electrons, but it has 4 valence electrons. 1, 2, 3, 4. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. Right? So that's why it's neutral. And the same thing for oxygen and 6 valence electrons. So if I take away an electron from carbon, nitrogen, oxygen, hydrogen, then you draw out like this. And you put a positive to show that one electron has been removed. Right? So I took out 1 electron, and now it doesn't have that 4th bond as a positive. Over here, hydrogen is positive. Over here, it's neutral. I took out that 1 electron. It's positive now. All right? Then same thing for ammonia and oxygen. The way I like to think about it, and if like you get a question like, what's the charge on this element? Just count the valence electrons. And then if it's less than the neutral charge, then it's positive. If it has an extra electron above its neutral, like valence electrons, then it's negative. And another way of drawing negative charges is you could just remove the electrons and then put a negative. Like how I put positive there, you can put a negative. So for oxygen here, I could just put a negative that shows that it has an extra electron. All right. You don't have to like study this as well. Like, you'll just get the hang of it as you just keep on seeing organic chemistry. And also, if you just know your valence electrons, then you're chilling. And oh yeah, so for carbon, you have to put a positive or a negative charge if it has 3 bonds, because you won't know if it has a positive or negative charge if you just leave it alone. So if I left this alone, if I left it like this, they're identical, right? So you have to put a positive here to represent that it's missing an electron, and then you have to put a negative there to represent that it has an extra electron. Because over here, if I erase this, and then let's say I erase electrons here, then you could be like, oh yeah, this has a positive charge because it has 4 bonds. And 4 bonds, 4 valence electrons. It's normally supposed to have 5. And the same thing there. All right. But you're probably going to get tested on this like once and then never see again. So it's not that important. And that's day 1. That's everything I learned on the first day of organic chemistry. 1 hour, 30-minute commute to class. 1 hour, 30-minute of being at class. 1 hour, 30 minutes for the commute back. All for this. And if you like my hoodie, that is shoparchive.com. Shoparchive.com. This video is actually sponsored by shoparchive.com. I'm low-key dying right now because the AC over here is not working and I'm wearing a hoodie. Okay. So next up, we're going to be talking about resonance and conjugation. All right. So I don't feel like writing this, but conjugation is the interaction of 3 or more p orbitals. Okay? P orbitals. So you guys remember p orbitals from Gen Chem 2? Yeah, that. P orbitals. And resonance is the movement of electrons in those p orbitals. Okay? Don't get them confused, because a lot of people get them confused, and you might get like a free response question on that. I'm pretty sure I did. But yeah. So I'll just draw out an example like this. Oh, okay, that's really bad. This marker is kind of dead, bro. Okay. Does this structure have conjugation? Oh, first, if this is your first time doing anything organic related, these dots, like edges, they just mean carbon. Okay? And then you're probably wondering, oh, carbon only has 1 bond here, but it's supposed to have 4, right? Well, you don't draw it out, but the hydrogens are invisible in these structures. So right here, there's 2 hydrogens that you don't draw. Over here, there's 3 hydrogens that you don't draw. Over here, there's 1 hydrogen that you don't draw. And then over here, there's 1 hydrogen that you don't draw. So you just don't draw out the hydrogens in organic chemistry. And the dots, the angles or whatever, they're carbons. All right? So is this structure here, is it conjugated? Well, this carbon is using its p orbital. This carbon is using its p orbital. And I don't know like the scientific background, but carbons that are positive, any carbon that's positive, it is always in the sp2 orbital. All right? Carbocations are always in the sp2 orbital, which means it has a free p orbital. So this carbon has a p orbital, this carbon has a p orbital, and this carbon has a p orbital. And now there's 3 p orbitals in this structure, right? So that means this structure is conjugated. And resonance is the moving of electrons. So now this carbon is positive, and we don't really like positive carbons. So what we could do is move this, the electrons in the in the p orbital, over here on this bond, to help out this positive charge. So it can now look like this. So now this carbon right here doesn't have a positive charge anymore. All right? And that's how it helps out. But now there's a positive charge here because it's missing its electrons. Its electrons move, you know? So that's what happens. All right? So that's resonance and conjugation. Oh yeah, and also this arrow represents like it's moving back and forth because it's a resonance form. Like that's what it means. It just means like this thing can become this thing and this thing can become this thing because it's about this charge. We could just go like this and it goes back there, right? So yeah, that's resonance forms. Okay? But now, I'm just gonna erase this. Actually, never mind. But now, there's this one molecule and has two different forms. How does that make sense? How can one thing be two things at once? Well, technically, the electrons are moving, right? That's what's happening. The electrons are moving. So let's just say my right hand is the electron, right? And let's say I'm the flash. So I'm moving my arm like this, up and down, up, down, up, down, up, down, right? And I can move it so fast, right? I can move it so fast, and you take a picture of me when I'm moving my hand up and down, up and down, up and down, right? If you take a picture of me, you're gonna see a hand that's blurry a little bit up here, and another hand that's a blurry a little bit over here, right? So I'm going, and then you take a picture. It's gonna be a blurry hand here, blurry hand there, right? That's basically how the resonance hybrid is. And the resonance hybrid is what's called the molecule's true form, if you will. So this molecule doesn't actually look like this. It doesn't actually look like this. It looks like a combination, like that example I was trying to show you. So what it actually looks like is this. Oh, this is such a bad marker, bro. Do you understand this part? Because I'm moving my hand so fast, you take a picture, you're gonna see two different hands. That's a little bit blurry. So these dashes are like the blurriness, if you will, right? So there's a bond there, there's a bond there. So there's two bonds, and they're both blurry. And now there's a charge here and charge here. So what you do, you just put partial positive and partial positive there. And that's the hybrid. This is how you study this molecule as like its thing. And then you put brackets just to show that it's a hybrid. So if you were asked, what is the orbital of this carbon? You could use this and this because they're the same orbital. But in higher, like more complex molecules that we'll get into, you can't use the resonance forms. You have to use the resonance hybrid because the resonance hybrid is like the true form. And okay, if you guys know Pokemon, if you guys know Giratina, the legendary Pokemon, it has an origin form and it has I forgot the other name, but it has like its snake form, the origin form, and then it has like its ground form where it's out of its like realm, right? So the origin form is like the resonance hybrid, its original form, and then the other form where he's like outside of his like space-time continuum, these are the resonance forms. You understand that? So if you're asked like, oh, how does Giratina look like? How does it actually look like? You would say the origin form, which is the resonance form. That's how I thought of it when I first learned it. And then when you're making resonance forms, you move one electron at a time. So you see how, you remember how I did that? You could just go back and see how I drew one arrow that represents the electrons moving. So you move one electron density thing at a time, if that makes sense. All right. Now we're going to get into this crazy of a structure. This structure was on one of my quizzes, I think. And this is a really good example and like problem to for you to like understand resonance forms, all right? So first off, is this thing conjugated? 1, 2, 3, 4. 4p orbitals, right? So yes, it is conjugated. So that means it could have resonance forms, right? And now, as you guys remember, nitrogen has 5 valence electrons, right? So it's hidden, but there's actually 2 electrons right there. But if you're wondering why I drew in the hydrogen when they're supposed to be invisible, hydrogens are only invisible when they're on carbons. So right here, there's technically 2 carbons, and right here, there's technically 2 carbons. Right here, there's technically, when I said carbon, I meant hydrogen. So there's 2 hydrogens here, there's 2 hydrogens here, there's 1 hydrogen here, 1 hydrogen here. But they're on carbon, so you don't draw them out. But if they're on anything else, then you draw them out. All right. So if there's 4p orbitals, what is the nitrogen, like what's its orbital? You'd probably say sp3, right? And I would say, yeah, right now it does look like it's an sp3 orbital, right? Because it has 1, 2, 3, 4 electron densities, and it doesn't have any pi bonds, right? But you can't use just a resonance form to determine the orbital the element is in. You have to use a resonance hybrid. So now let's draw it out, the resonance forms. So what I like to do, I'm not sure if this is like the correct way, but normally the way I do it is if there's an oxygen, I usually just pull up the electrons to the oxygen like that. So then, and also one at a time. See how I do that one at a time? Because I can also do this and this too. But we're doing one at a time because you're gonna get counted. Like your points are gonna be counted for each resonance form. And if you skip a resonance form, you're gonna get minus points. Let me just check to see if the sizing is good. Okay, there's a little bit glare. Is there a way to turn it off? The glare is still there. You guys could work with it, right? It's fine. Actually, I'll just move it. So I'm just gonna redraw this on the left side because this is probably worth like 15 points if you see this on your exam. So I'm trying to save you 15 points, bro. Yeah, this is better. So now I'm gonna draw out the next resonance form. And now that this oxygen has an extra electron, it's now negative, right? And sometimes when I'm drawing out pi bonds, I like to put out the pi bond outside like this. You could draw it either way, inside or outside, but I like to just do it outside. It just helps me visually. And then there's electrons right there, because nitrogen has 5 valence electrons. And now, what we could do is move those electrons to this bond, because I forgot to draw something. I forgot to draw a positive right here. Because if the electrons over here are now on the oxygen, then this carbon right here, it doesn't have like an electron, right? It's missing its electrons from that pi bond. And if I drew out like this, if I forgot that, well, I did forget that. But this means that there's a hydrogen connected to that carbon, right? So that's why it's so important to draw out the positive charge. And also, the charges are still maintained. So this is neutral, right? This is also neutral because it has a minus and a positive charge. So now we can move this pi bond, like the electrons. I'm just gonna say pi bond because I'm removing the pi bond. I don't want to be too like grammatically correct because this is all about like understanding organic chemistry. So if you get me, then you get me, you know? So I'm gonna move that pi bond there to help out this positive charge because we don't like positive carbons, right? So now another resonance structure is right here. All right. So now we're done, right? We're done with its resonance forms. No, we're not. Why? Because there's electrons at this nitrogen. And what could those electrons do? It could help out this carbocation, right? So it's going to donate its electrons and form a pi bond. Wait, is the glare there? Okay, I'll just draw it really big. So now it's going to form a pi bond, that nitrogen. Right? So now that nitrogen formed the pi bond. And now, how many valence electrons does nitrogen have? Now has 4. So this is now positive. All right? So charges are still maintained. And now, going back to that first question, what's the orbital of this nitrogen? sp3. Well, what is the orbital of this nitrogen right here? sp2, because it has a p orbital. It's making a pi bond. So what is the orbital of this nitrogen? Is it sp2 or sp3? It's sp2. Why? Because we have to use a resonance hybrid. We have to draw out the hybrid form of this guy right here. And the way we do that is, again, remember that picture diagram thing I was trying to do? The Giratina origin form thing? That's what you do. You draw out the resonance hybrid. So when you study molecules, you have to use the resonance hybrid because you could see this on your test, just this structure right here, and it's gonna ask you what's the hybridization, the orbital or whatever of the nitrogen. You're gonna say, oh, sp3, but you have to drop the resonance forms, and then you drop the resonance hybrid. You don't really have to. You could just study it this and like just imagine in your head. But basically, what I'm getting to is you have to use the resonance hybrid to determine the orbitals, because this is how it actually looks like. So if this is negative right here, this oxygen's negative, but it's not negative here. Then what is this? This is partial negative. And then there's no pi bond here. There's no pi bond here, but there's pi bonds right here. Then you put dashes. And then there's a pi bond there, no pi bond there, no pi bond there. Then you still put dashes. And then there's no pi bond here, there's no pi bond here, there's no pi bond here, but there's a pi bond there. So you put dashes right there. And then what am I missing? I'm missing the positives. All right, sorry, bro. I've been having some allergies lately. I really don't know what's going on. But like this allergies things never happened to me before. I got like the fluctisone spray thing. I think it's been working. But I just wanted to get this video out before school starts. So, and this topic isn't really that important in the grand scheme of organic chemistry. I mean, it is important, but it's pretty easy to understand if you just go to your professor's like office hours or just attend class normally. But for the first like month of organic chemistry, you're just gonna learn about this. And if you spend a month on this topic that I just explained in like what 2 minutes, then you're gonna get the hang of it. All right. And also, I forgot the brackets. So these are the resonance forms, and this is a resonance hybrid. This is how the molecule actually looks like. That's how you're supposed to study. And again, I'm going to say this for the last time because, like, so many people during class, they'll be like, why did I get this wrong? Why did I get this wrong? Well, the question was this. It was literally this exact question. It was, what's the orbital of this nitrogen? And they'd say, oh, it's sp3. And then you drop the whole thing and it'd be like, oh, it's sp2 now. So it's sp5 because 2 plus 3 equals 5. No, you have to use the resonance hybrid. It has a charge here and it has a pi bond there. So it has a p orbital and it's sp2. All right, I feel like I'm mansplaining, so I'm sorry about that. I should just be a woman next time. No, I'm playing. Shout out to women. All right, why did I say that? But basically, this is what like all of September is if you're taking organic chemistry this fall. So that was basically one of the hardest like resonance form questions I got. So you're probably not gonna see anything more than that, unless like you're in a higher level or I don't know something. But that's basically it for resonance forms, and you just have to remember how to do all that throughout your organic chemistry because sometime in organic chemistry too, you're gonna have to like draw out resonance forms and see which one is more stable and all that. We're not gonna get into it right now because I don't feel like teaching it, and we don't learn that until later. So, yeah. All right. So the next topic is acid and bases. So you guys remember from Gen Chem your favorite acid-base reaction? HA, hydrogen and an acid, plus B, which is a base, and then it's an equilibrium. And then instead of drawing the dots, like electrons, you could just put a negative, right? And then you're probably like, oh, this is the conjugate acid, this is the conjugate base, this is the acid, this is the base. You don't really need to use that in organic chemistry. Like the terms are not really that important, but if you know it, good for you. But you don't really need to, like, they're not going to ask you that question. Maybe on the MCAT, but not in organic chemistry. So now you guys know this reaction, but how do we know which side is more like favorable, right? So to know which side is more favorable, we have to know the pKa's of the acid. All right. So basically, the pKa is a range of numbers that represents how strong an acid is. So let's just say you're not going to see this really, like these numbers, but just for example, let's just say you have an acid that has a pKa of 100. What does that mean? It means it's at level 100, so it's the strongest acid, right? No, it's not. Because if you guys remember pHs, pKa and pHs are basically the same thing. So I'm just going to say that they're synonymous, but your professor might get angry at me if he catches you say that. But in this sense, pKa and pH are basically synonymous. So if the pKa is the level, like the strength of the acid, that means a lower, and okay, forget everything I said about this. Okay? Just remember that pH and pKa are the same thing, but pKa is just of the acid. All right? So if something has a pKa of 0, that means it's a really, really strong acid. All right? And if an acid has a pKa of 100, that means it's a really, really, really weak. It's weak. It's a weak acid. So weak acid, strong acid, right? So if something, okay, so then why is this important? Why is pKa important in this reaction? Because that's how you determine what side is favorable. Let's just say this acid has a pKa of 10. All right, and then now what? This is like the conjugate acid or whatever, but basically has a hydrogen. And if you guys remember, something can donate a hydrogen, it's an acid. If something accepts a hydrogen, it's a base. That's like Gen Chem. There's probably like a better term for it, but you don't really need to know that. And let's just say this conjugate acid has a pKa of 50. So which side is more stable? Which side is more stable? So if this acid is such a strong acid because it's lower than what we said over here, if this acid is stronger, then this reaction is going to go more this side, right? And if this is a weak acid, because it's 50, and it can't really donate its hydrogen as well, then it might go a little bit like this. It might go a little bit to that side, right? Well, what side is more favorable? Because if this donates the electron super good, and this one donates, like it doesn't really donate the electrons that well, I mean not electrons, hydrogens that well, then it's going to keep it. It's going to stay on this form. So what we basically say is, if something has a higher pKa, like if you're looking at this reaction, like an acid-base reaction, and you see something has a higher pKa, then that higher pKa side is the more like favorable side. It's gonna, this reaction chart right here, that's in equilibrium, it's more gonna be to the right because we like stable things in life. We don't like reactive things. All right, we like things to be stable, and for example, I like to just sit in bed all day. So this is what basically this hydrogen is doing. It's sitting in bed all day. B for bed. And then hydrogen next to an acid A that has a super low pKa, it's active. It's moving around. And me, I don't like to be active all that much. I like to stay in bed. But the A and B, what I said, the active and staying in bed thing, it doesn't really apply because this is just an example. Like it's not going to be A and B. It's going to be like oxygen or something, you know? So that's basically it for pK, like these acid and bases. To see which side is more favorable, you just find out which side has a higher pKa. And a higher pKa means it's it's not gonna give its hydrogen away as much, which means it's a weak acid. Higher pKa, weak acid, it's not gonna react. All right, and you're probably wondering, oh, how can I figure out the pKa of something? Well, you have to memorize it, which is the unfortunate part. And yeah, that's kind of the hard truth about this topic. You're just gonna have to memorize the pKa's of all your acids. Your professor is probably gonna give you a chart, and I'm trying to. Okay, let's go over it. So basically, anything with a nitrogen and like a hydrogen of somewhat, like a nitrogen hydrogen derivative or something. The way I memorized it is basically anything with a hydrogen, it's gonna have like a pKa of like 35 or 38. And then if it's ammonia, which has a positive charge, then I think it's like 10 or something. Listen to professor on that part. So that's how like anything with a nitrogen that's not ammonia or ammonium or whatever, the one with the positive charge, that's gonna have like a pK of like 35. And then the way I memorized ketone, so this is ketone. The way I memorized this has a pK of 20, and it's called a ketone. So people start a keto diet when they're 20 years old. So that's the way I memorized that. And then this is alcohol, your OH group. This is alcohol. And then R. Oh yeah, if I didn't mention earlier, an R means that it's bonded to something. So this R group could be a carbon, it could be anything. So it just shows what's at the opposite end of the bond. So this is alcohol. And people typically they start drinking alcohol when they're 15. That's like the first time that they drink alcohol, right? At some high school party. So alcohol is 15. That's the pK of alcohol. And then I think water is not water. Yeah, water is also 15, I think. Don't quote me on that. And then hydronia, which is like this one is 0, I think. But your professor is going to give you a chart and you just have to memorize the pK numbers on that chart. But let's say your professor is really mean and he makes HA, B, A, HB, some random compound that you've never seen before. It's not a ketone, it's not alcohol, it's something random. But you know that it has a hydrogen and it's donating hydrogen. And now this is the acid, and now this is the acid, this is the base, and this is the base of this side, or whatever, right? So the way you could figure out what side is more favorable or like stable is by examining its base, because the pKa and everything that was of the acid, it was of the acid, right? But if you don't know the pKa's of the acid, then you examine the base. The base, right? And the way you examine the base is by looking at 4 features, which is the element. And these features are effects. So these 4 effects. So there's the element effect, the inductive effect, the resonance effect that we just went over, the topic that we just went over, and then hybridization. So basically, the element effect is the more electronegative element will be more stable with electron density. All right. I don't have examples, so I'm sorry about that. So I'm just gonna say them, like their definitions are. And then if you go down the column of the periodic table, so let's just say you're comparing this A and this B, and the only difference is like its periodic trend. So let's just say this is A and this is B. If you're going down the column to determine what, oh, no. This A is representing of this, and this B is representing of this, because we're looking at the base effects. That's how you get mixed up, right? Because everyone, they always get confused. Even me, I get confused about it too. I just did right now. So HA is the acid, HA is acid, HB is the acid, and then B minus, A minus is the base. And for these effects, these features or whatever, you examine the base. So if A is higher on the periodic table and B is lower on the periodic table, then what you do is if you're going down the column, then you go based off the size. So if you're going down the column of the periodic table, then the element has a bigger size, which means it can hold more electrons. So if we're examining this reaction and B is more down on the periodic table, it means this could fit more electrons because it's a bigger element. All right? So the left side would be favorable if this was the case. All right? And then the inductive effect is nearby electronegative elements can induce a pull on the electrons and stabilize the base. Right? So like the thing with the negative charge. And then the resonance effect is bases are more stable with resonance. And then hybridization effect is orbitals with more percent S character is more stable because the electron is closer to the nucleus. So let's just say we have a double bond, R group, and this thing is negative there. And we're comparing it to this thing right here. What base is more stable? It's this one, because this one has more S character. It's SP, this sigma bond is sp2, which means it has more S character than P character. Because sp3, it mixes all the p orbitals with its S, right? An sp2 orbital, it only mixes like, what, 2 out of the 3 p orbitals? So this one has more S character, and that means these electrons are closer to the nucleus, which means it's more stable. That's what the hybridization effect is. And I know I'm not that good at teaching this thing because it just came kind of naturally to me. So I recommend everyone to watch Chad's prep video on this topic. He explained it very well, and he has examples and everything that he draws out. I don't have that power. Chad's prep is the GOAT. I think I watched that video of the bases and their effects like 500 times. So I'd say watch that video a million times over, and you'll be a master at understanding the base effects. All right. And all right, yeah. I'm gonna stop this video right there. Thank you so much for watching my first video. And I'm gonna link the Chad's prep video in the description. Make sure you watch that so you can understand the base effects. I think I taught the acid effects pretty good. I mean the acid effects, the pKa thing, pretty well. But please watch the base video that Chad's prep made. That is one of the most legendary videos of all time. All right, thank you so much for watching.